In this video, I would like to speak some words about the eigenvalues and the meaning of the eigenvalues, because in the last I showed you the open loop system and the closed loop system, and we spoke about some desired lambda tilde and how to choose lambda tilde, why we really need new eigenvalues of a closed loop system if it is really necessary. So in this video, I would like to make it a little bit more clear. So these are the eigenvalues, because we have got a characteristic polynomial phi of lambda. It is lambda multiplied by the identity matrix minus the A matrix and the determinant of it. It's a polynomial. It's an n-order polynomial. And from this, if we can solve this polynomial equal to 0, we can get the eigenvalues lambda 1, lambda 2, etc., lambda n. And there are some lambdas. Lambda can be a real number, just a pure real number. Lambda can be a complex number. In general, it's complex, of course. It can have a positive real value, negative real value, and so on. And these eigenvalues which I draw to the complex plane. So in general, lambda is in the set of the complex numbers. So that's why we are going to draw the eigenvalues on the complex plane. This is the real part of lambda. This is the imaginary part of lambda. And the left hand side of the complex plane is the stable lambdas when the real value is negative, and this part is the unstable part when the real part is non-negative. And I show you some very simple examples. If our lambda is here, the transient behavior of the system usually an exponential function which looks like this. Let's say it's y, doesn't matter, y transient. If our lambda is larger in the negative case, it means that our transient will be much faster, like this one. So if we move our lambda with a larger value on the stable part, for example from here to here, so if we move our lambda to that value, our transient will be faster. So one very good idea is that, so if we have got a transient and we don't like this transient because it's too slow, we can make it faster if we choose another lambda with a larger value in the negative case, of course. This transient will increase to infinity like this. We cannot work with it. So if we have got an open loop system which is not stable, we can do it stable if we choose a more clever lambda like this one. So we can move our unstable lambda to the stable one. So if we choose, for example, our lambda is positive 2, we can choose negative 4. It will be stable and fast. And with another color, if you have got a complex, really a complex value of the lambda, for example, this lambda and this lambda star, because of the conjugate value, so the real value is the same and the imaginary value is a negative value of the other one. So we can, if we don't like this transient, because our transient in this case will be a sinusoidal transient like this one with decreasing amplitude. If we don't like it, we can do that. Let's change these eigenvalues to a real value, for example. Or we can choose a faster eigenvalues like this. We can move these eigenvalues with a larger real part. Of course, we can modify the imaginary part too. So the basic idea of state feedback control is that if we don't like any of the eigenvalues of the open loop system, we can change it. How? We can make it faster, we can make it stable, we can prepare sinusoidal transient, or opposite, if we don't like the sinusoidal transient, we can choose a real value for the eigenvalues, and so on. So any of the lambdas which we don't like, we can choose another one for the closed loop system. This is the open loop system lambda, and this is the closed loop system lambda, which we would like to have. And our goal is to reach these lambda tilde, and we can do it by appropriate selection of K transpose. And this is what we are going to do in the next videos.